Now I'm going to show you an interesting looking theorem which tells you that you can find, like, in any coloring of the whole space, like a plane, no, not plane, yeah, I mean, okay, in any coloring of the plane, for instance, I can find exact shape. Like if I draw 5 cones like this, then somewhere I can find these 5 points in the exact same way. What do I mean by exact same way? So let me say as follows. So let's say V is V1, V2, and Vt is a subset of the vectors in Rm. We say W is homothetic to V if there is an ordering of W of vectors in W, let's say W1, W2, Wt, such that, oh, and also, okay, I should say there are n vectors A, vector A, okay, and A in R, M and B in R, and B such that Wi is equal to A plus B V. A plus B times Vi for all I. So basically, you have a set of vectors V. I'm gonna translate. I'm adding same vector A, so I move to somewhere, and then I scale by B, right? And then that set of vector is homothetic to integer set of vectors. So in this case, I move these 5 points to the right, and then I scale them by multiplying, let's say, 2. Now, here's an interesting theorem due to Gallai. For every coloring of Rm into finitely many colors, and for every finite set V in Rm, there exists a monochromatic set W in Rm homothetic to V. So no matter how I color the whole Rm by finitely many colors, there exists set of points which is homothetic to my fixed set V, and this set have the same color everywhere. This is very strange, right? And you can think of it as, and we can prove it by using van der Waals theorem, but I'm going to show you the proof by using the Hertzsprung theorem. So let R be the number of colors, okay, and let T be the number of points in V. Let N be the Hertzsprung number of RT. No, The other way around, right? Number of colors is always at the end, so TR. Alright, so let's pick a function from this k to the n to q to Rm, so that this function is simply a linear combination of them. Vi Vxi. Right. Oh, what is V? So V is x, V1, V2, Vt. Oh, I'm confused. Yes, so right. I'm just, let's not use t, let's use k. All right. Now, this is a mapping from set of set of points, sequences in k to the n to the real space. Right. So if, for instance, if x1 is 1, 1, 1 goes to like c1 plus c2 plus c3, no. c1x1 plus c2x, c1v1, c2v1, c3v1. Right. Something like this. Now, we didn't decide the c1, c2, cm. Now, if we can choose c1, c2, this coefficient, so that this function is injective, then from the coloring of Rm, we have an R coloring of this cube, right, k to the n. Because it's injective, there's no ambiguity, right? You can decide, you can choose the color based on the color of the image. Then there is a monochromatic combinatorial line, and that means you're gonna have C, yeah, so you will have something like this, where this is a linear combination, all right, let me say it this way. Vi, where I is 1 up to 1 up to k, right? So it's a set of points of this. So this first part is corresponding to the segments where it doesn't have star. This part corresponds to segments with the star. Stars are replaced by Vi, right? So all of them have the same color. Maybe it's easier to explain by example. So for instance, if I have a 1, 2 star, that means I have C1 C2v1 plus C2v2. Now, let me give a different example. So C1v3 plus C2v1 and star is replaced by C3v1 and C3v2, C3v3. Right? So I'm gonna take this part as my A and this part as my B. Then A plus B VI become WI, and all of them have the same color because it's combinatorial line. So W is like A plus B VI, where I is from 1 up to K. Is a monochromatic. All right, so that's easy consequence of the Hastrecht theorem if we can find this coefficient. So how do we choose C1 up to CK so that this function is injective? Well, almost all choices will work because what we want is Ci and Vxi minus Vxj. Well, xi prime is non-zero for all like x for all x and x prime in k to the n. And how do we know such a thing? Well, the thing is, well, we need to avoid having equality, and the number of equations is finite. Right? The number of equations is finite, so there is a choice, C1 up to C, and to avoid all of them, right? You have a finite many linear equations, right? So in the geometrical term, it's like you have a set of hyperplanes to avoid, right? And you need to select a random, some point outside of that, right? For instance, I can just take a random set of random number, and the probability that I hit this equality is 0, right? And you only have finitely many equations, so almost all choices will work. And in this proof, you can actually see that so this is the end of the proof. We can make sure that this function is injective, and as soon as it's injective, then you're done. All right, and here's a corollary. Here's an interesting corollary, which looks quite non-trivial. So let n is this set of positive integers, and if n squared is finitely colored by finitely many colors, then for each T, there exists x0, y0, and D such that x0 plus ID and y0 plus JD for all I and j from 1 up to 0 to T have the same color. So you can have a, so this is like, you can find something like a grid. No matter how I color the whole plane. Oh, by the way, I didn't color all the reals. I only colored the integers. Why can I do that? Well, the thing is, if you look at this proof, I can choose Ci to be integers. Right? I mean, I can choose, let's think of this way. I can choose Ci to be rational numbers. Right? If there's, and then if once you have rational numbers, you can multiply some big number so that everything is integer. So once you choose Ci to be integer, then all these coefficients will be integers. So therefore I can choose A and B to be integers. Right. So basically we can, and also I can choose and I can choose this C to be positive integers. There's no need to use our goal is to just make everything injective. So and you can choose these to be positive integers, and then that means there's a homothetic set where this B is positive integer. Alright, and A is positive. Suppose A, B are positive integers, and therefore I can find such a thing. So you can think of this as a multi-dimensional version. Not only you have a one-dimensional arithmetic progression, but you can have a multi-dimensional arithmetic progressions, right? And this, and n square, you don't need the n square, you can have an n to the t, right? If you color the t tuples of integers, positive integers, you can always find this kind of multi-dimensional grid with all the same color. All right.